Hello. Hello.
Yes, sir.
Yes, sir.
Okay. So let's go ahead. Mm, okay. So let's start. So I have discussed about radiation from accelerated point charge in case of non-relativistic velocity and also relativistic velocity, and that is we have already discussed about Larmor formula and the Leonard radiation formula, and we also discussed about the radiation angular distribution of the radiation in non-relativistic case and also in the relativistic case, particularly when velocity and accelerations are perpendicular. So let me just briefly summarize what we have learned in the previous class and then move forward. So I am just giving a summary, brief summary. I mean, what we have discussed in the last class. So we are discussing about radiation, specifically the angular distribution of radiation from accelerated point charge. So I'm not writing here the Larmor formula or Leonard formula. I will just discuss about the angular distribution right now. So what was our approach? We calculated the power radiated per unit solid angle, per unit solid angle. And what was the formula for it? So we calculated dp d omega in this way. What is that? So power radiated per unit area, if you remember that, power radiated per unit area, and then we multiply with the surface area of the sphere 4 pi r square and divide by the total solid angle 4 pi. And the formula for this one we have already derived this one, right? So this is given by the Poynting vector sr dot r cap into dt dtr. You may remember this two different time. T is the time in the observer's location and tr is the retarded time, right, which is associated with the point charge from where the radiation is emitted. And so if I multiply this 4 pi is not there, so we have just r square here, right? And this thing is also calculated. If you remember, I'm not repeating that. So dtr dt, this was calculated in the last class, which was 1 over 1 minus r cap dot beta. And we also calculated this one sr dot r cap, which was 1 over mu 0 c, and then er square. R cap is the direction of the Poynting vector dot r cap, which is 1. So just have to square of this. And er is also known to us. What was er? Okay, let me write down er again. So er is the radiation field associated with the accelerated point charge, which is given by q by 4 pi epsilon naught c times r cross r minus r beta cross beta dot divided by r minus r dot beta whole cube. Or you can also write down this in terms of the unit vector q by 4 pi epsilon naught c, and then r cap cross r cap minus beta cross beta dot divided by yeah, there will be r here, 1 minus r cap dot beta whole cube. So we just have to put this expression over there to calculate er square. So I am not repeating the entire calculation. I'm just writing the result here. So if you just plug this in and you calculate this er, so this will be how much? Okay, let me just write down it. 1 by 4 pi epsilon 0 q square by 4 pi c. This is straightforward, 1 by r square, and then whole of this one r cap cross r cap minus beta cross beta dot divided by 1 minus r cap dot beta whole cube, square of this entire thing, right? So then if you plug this in here and put the value of dt dtr, which will be inverse of this is 1 minus r cap dot beta. So then we get dp d omega, dp d omega power radiated per unit solid angle is given by 1 by 4 pi epsilon 0 q square by 4 pi c, and then r cap cross r cap minus beta cross beta dot square, and this was cube, so this would be 6 1 minus r cap dot beta to the power 6 6. And we simplified this based on the condition that the case that was analyzed in the last class was when the velocity beta and acceleration beta dot were parallel, so collinear velocity and acceleration. In that case you see, in that case beta cross beta dot will be 0. So you can simplify this entire expression, and what we got was dp d omega equal to 1 over 4 pi epsilon 0 q square a square by 4 pi c cube, and then what was that, sine square theta, sine square theta or cos square theta, I don't know, it was sine square theta, right? Sine square theta divided by 1 minus beta cos theta whole to the power 5. So this was the expression for the angular distribution of the radiated power from an accelerated point charge when the velocity and acceleration are parallel to each other. And we discussed about the radiation pattern. In the non-relativistic case, the entire radiation is emitted in a direction orthogonal to the direction of the acceleration in a form of a donut, which I have discussed. So in the non-relativistic case, it looks like something like this, right? This is the direction of acceleration beta dot, this is angle theta, right? And this is the direction, orthogonal direction along which the power is emitted. So no power is emitted in the forward or backward direction. And when we go to relativistic scenario where beta is of the order of 1, this is the case when beta is much less than 1. When beta is of the order 1, what happens, this entire this donut bends forward, so in the form of a cone, and this gradually happens as you gradually increase beta, this will gradually bend forward. So this is beta dot, and the distribution in the form of a cone. This is two-dimensional. You can see a cone here. It is actually a cone, and when beta is almost around 1, the entire radiation is basically confined in a narrow cone in the forward direction, in the parallel to the direction of the acceleration. So this is the distribution of the radiation from an accelerated point charge for collinear velocity and acceleration. So for today's class, what we are going to discuss is the same thing, but when velocity and acceleration are perpendicular to each other, orthogonal. So, so all of you can guess, I mean, the difference between these two, because velocity and acceleration, I mean, it can happen when, say, a particle is moving along a straight line. So velocity and acceleration are parallel, of course. But suppose the particle is not moving in a straight line or in a straight, I mean, linear path. It is moving in a circular path, suppose. So in case of circular motion, we have velocity is tangent to the circle and acceleration is towards the center. So they are orthogonal to each other. So we want to know what kind of radiation pattern we expect to see from the accelerated point charge. So a particle which is moving around a circle, so that is accelerated, right? Even if you keep the velocity same, it's accelerated. So for any accelerated motion, we expect some radiation from that point charge, because that is what we see from the Leonard formula. And also that is obvious because radiation field, I mean, is non-zero. beta dot term is non-zero. So acceleration will produce some radiation, and we want to know the radiation pattern. I mean, which direction will get the most of radiation and which direction will get no radiation, and so on. So let us analyze that. So we have this formula which you have to remember here, this formula. So I am not going to derive it again. So this is the formula that we will start with. This gives us the power radiated per unit solid angle. So let us start with this formula. And so we have this formula, power radiated per unit solid angle. Let me write down the formula first. dP d omega is equal to 1 over 4 pi epsilon 0 q square divided by 4 pi c, and then r cap cross r cap minus beta cross beta dot acceleration square divided by 1 minus r cap dot beta to the power 5, because this was 6 and you have to multiply with 1 minus r cap dot beta, if you remember, because dp d omega, what was dp d omega? Let me just remind you. Dp d omega, probably I forgot to cancel this power. Dp d omega is r square, and then r square is r dot r cap into 1 minus r cap dot beta, right? So this quantity, this 1 minus r cap dot beta, and we have a 1 minus r cap dot beta to the power 6 coming from this sr dot r. So that will the power will be reduced by 1, right? This is the formula for the power related per unit solid angle. And so you want to analyze this case when beta, that is first say like the case when velocity and acceleration are orthogonal, right? So what would be the dp d omega then? And so what is that we have to calculate. Now so let us start with this formula and how to simplify this formula, right? Earlier, what happened in case of parallel motion, velocity and acceleration parallel, beta cross beta dot was zero when beta and beta dot were parallel. But this time it is not going to happen. So earlier we had r cap cross beta dot, but this time we have to deal with all the terms, right? None of them will be zero. So let us first simplify this term on the numerator, and then I shall come back and use this formula again. So let us write down this. So you want to simplify this. What is that? R cap cross r cap minus beta cross beta dot square. What is that? Right. Okay. Let us draw a picture first. We want to visualize, I mean, what is the direction of beta dot, and so on. So let us choose a coordinate system. This is a simple coordinate system, Cartesian coordinate system, where I choose this to be x, this to be y, and this to be z, right? Now imagine a charge particle which is moving in a circular path, and the circle is lying on the xz plane. Okay, so it is difficult to draw that circle. So what I'm drawing only a part of the circle, that is the arc, a particular arc. So suppose the circle goes like this, touching the origin. So it's a one part of the circle. So this circle is actually in the xz plane, and you can see, understand, this xz plane is perpendicular to the screen, right? YZ plane is the screen, xz plane is perpendicular to the screen. So this circular path, this trajectory of the charge particle is touching the origin, and then this is coming like this, and this will complete a circle, right? If that is the case, you see z axis. So at this origin, this circle touches the origin. So at this point, it's a tangent. Z axis is a tangent to the circle, right? So velocity is pointing towards this, right? This is the direction of velocity. And at that instant, the acceleration is basically pointing towards the center of the circle. So that is lying towards the x-axis. So acceleration is along this direction. This is acceleration. This is velocity. This is acceleration, beta dot. And we want to know the angular distribution of the radiation. Now when you choose a coordinate system like this xyz, a Cartesian coordinate system, we have to label the position of any point in space using different uh, coordinate xyz, or say r theta phi, whatever you like, right? So if we use, see, in general, it is useful to use spherical coordinate, because we are using r theta and phi earlier when we integrated to get the power radiated. The theta is there, so it is useful to stick to this spherical coordinate system. So any, suppose we want to know what is the radiation along this direction or that direction or that direction, so on. So let us just draw one particular direction, say suppose this direction. So just call this is the direction r cap, right? So this is the charge particles. You may remember what is r. This currently r is, this is the direction from the field point, sorry, the source point to the field point, right? This vector is called this currently r, this radius vector. And once you define r this way, so then basically in spherical coordinate system, this theta angle is defined with respect to z axis. So this becomes theta, this becomes theta. And if you drop a perpendicular on the xy plane, what you have is basically this one will be, this angle will be phi, this angle will be phi. So theta, phi, and r, these three things define the position of any point in space. And we have a circle which is lying perpendicular to the screen, and we want to know how the radiation from this accelerated charge particle will look like. So we want to first simplify this expression. So let us simplify this. For the time being, I'm defining this to be a new variable. So let's call this to be y, or any z, or I think, yeah, any variable you can define. Y, it's a r cap minus beta. This is a new variable, and we define it for this for simplicity, because you don't have to deal with them separately, because then I have a cross b cross c, and the product will be simpler. So just for the sake of simplicity, r cap cross, say now it is, I am writing y cross beta dot square. We want to simplify this. So it is in the first step, we just take a cross b cross c. So I write y r cap dot beta dot, right? This is acceleration. Remember, this is acceleration. Beta dot and minus beta dot into r cap dot y square. So this is just a minus b square, nothing else, equal to y square into r cap dot beta dot square, a square plus b square beta dot square into r cap dot y square, a square plus b square minus twice ab twice. So we have three terms, r cap dot y, y dot beta is there, y dot beta dot, and then r cap dot beta dot, r cap dot beta dot, and then we have r cap dot y, r cap dot y, whole of this square. Sorry, square is already simplified, do not have any square. We have already done this one. A minus b square is this one, right? Now let us simplify each of these terms separately. So what is r cap dot beta dot? What is r cap dot beta dot? Tell me. What is r cap dot beta dot? This is r cap. That's why I have drawn this diagram. So to simplify this is r cap, right? And what is the direction of acceleration? Along the x-axis. So what is r cap dot beta dot? R cap is the magnitude of r cap is 1, right? So what is r cap dot beta dot? Simple coordinate geometry. Can you hear me? Hello.
Yes, sir.
Okay. So what is r cap dot beta? So you know both the direction. R cap is this, beta dot is this. So how do you go from r cap to beta dot? How, you want to take a dot product, right? You see, this angle is theta. This is cos
Sir,
theta.
minus beta dot sine theta cos phi.
Why minus? Why there will be minus?
Sir, 180 ডিগ্রি minus phi যখন নেব, না স্যার, না স্যার,
No.
প্লাস হবে স্যার, প্লাস।
Right, right. Plus ही হবে. Beta dot. You are correct. Beta dot. This is the direction of acceleration beta dot, right? And this is r cap. So r cap. This is cos theta. This is sin theta, right? So sin theta and then cos phi. So beta dot sin theta cos of phi. This is r cap dot beta dot. What will be y cap? Oh, acha, আর কি আছে? r cap dot y. আচ্ছা, এটা কি হবে? This is simple. R cap dot y, because we know what y is. R cap dot y is what? Y is this one. Y is r minus beta. So r cap dot r cap is 1, 1, and then minus r cap dot beta. What is the angle between r cap and beta? Theta. So that will be simply beta cos theta. So 1 minus beta cos of theta. So this term is okay, done. This one is also done. So we have another two terms, right? This one, another term, y cap dot beta. This one, this two is already done. R cap dot beta, r cap dot y. Yeah, y dot beta dot. So what is that? That is basically beta dot. So dot product, I can change the order. Beta dot into r cap dot beta. Now beta dot, so this will be basically beta dot
Sir,
r cap,
r cap minus beta.
r cap, yeah, this is r cap minus beta, correct. Beta dot r cap minus beta dot beta, right? Yeah, and this will be 0 since they are orthogonal, so only this term survives. So beta dot r cap is same as this one, right? So they are actually same. This will be again also beta dot sin theta into cos phi. So I think we have already calculated all the terms. আচ্ছা, আরেকটা টার্ম আছে y square টা কত, এটা বার করে নেওয়া যাক। y square is simple. What is y square? Y square is r cap minus beta dot r cap minus beta. So basically this is a just dot product. So r cap dot r cap is 1, beta dot beta, so minus minus plus, so 1 plus beta square, and then we have a two r cap dot beta term, so twice r cap dot beta term. R cap dot beta is already known to us, so this is basically 1 plus beta square minus twice beta cos theta. So now we have all the ingredients with us. We just will substitute these into this expression and simplify to get the numerator in this expression, right? dpt omega. So let us do that in the next page. Okay, so I'm not okay, maybe I should write it or maybe not. Okay, what was the expression? Let me just write down that. So we wanted to calculate this one, r cap cross y is basically r minus beta dot, so beta dot square, where no, y equal to r cap minus beta. We wanted to simplify this, so our expression looks like this: y square and then r cap dot beta dot square plus beta dot square into r cap dot y square minus twice y dot beta dot into r cap dot beta dot, yeah, into r cap dot y. And we have already calculated the simplified expression for all of this, so we'll just substitute them in this expression. Okay, so let us substitute that. Okay, so so we have already calculated y square, so I'm substituting the value of y square first. So y square was how much? Y square was 1 plus beta square minus twice beta cos theta. We just calculated this one. and then r cap dot beta dot, r cap dot beta dot is beta dot sine theta into cos phi square. Okay, first term is done. Second term is this one, plus beta r cap dot y. I think r cap dot y is 1 minus beta cos theta, right? And beta dot square, so beta dot square into 1 minus beta cos theta whole square. And then we have these three terms, so two of them are exactly identical, so which will give us minus 2 into beta sine theta cos phi. Both of them are same, right? This one and this one, so this will be square, and then one is 1 minus beta cos theta. Yeah, 1 minus beta cos theta r cap dot y, this one. Then you see all of the terms contain beta dot square, beta dot square, beta dot square. So I'm just taking that outside, beta dot square taking outside. So inside that also sine square theta cos square phi is there with this term and this term. So let us make them separate. Sine square theta cos square phi from the first term and the third term. I'm taking sine square theta cos square phi common. So that gives us 1 plus beta square minus this twice beta cos theta, this whole thing twice beta cos theta, and then I have taken so this common, so minus 2 minus plus 1, so this becomes minus 2 minus beta cos theta, minus plus twice beta cos theta, and then what is left, this one, plus 1 minus beta cos theta whole square. Beta dot square is taken outside. So plus 2 beta minus 2 beta cos theta plus 2 beta cos theta are cancelled, and this minus 2 and plus 1 becomes minus 1. If I take a minus common, then to become 1 minus beta square. So we have now beta dot square into, I am writing this term first, so 1 minus beta cos theta whole square. I'm taking a minus common. 1 minus 2 is minus 1, so minus 1 is taken outside, so that becomes 1 minus, this was minus 1 plus beta square, that becomes 1 minus beta square. And then we have this one, sine square theta cos square phi, right? This is the numerator of that expression, if you remember. Now let us write down the entire expression together. So dp d omega, what was that? That was 1 by 4 pi epsilon 0 q square a square divided by 4 pi c cube, and then the entire expression that we simplified, this r cap cross y, or this thing cross beta dot square divided by 1 minus beta cos theta whole to the power 5. So this has been already simplified, and beta dot square that is written as a square by c square. So I have taken this a square here and c square in the denominator, which had there was a c earlier, so c square and c becomes c cube, and I am writing this rest of the terms here. So this will becomes 1 minus beta cos theta whole square minus sine square theta cos square phi into 1 minus beta square divided by, this was already there, 1 minus beta cos theta whole to the power 5. Okay. Now how to visualize this? What should be the radiation pattern? You see, it is not easy to visualize because we have two different things, two different angles, theta and phi, right? One is theta and then phi. And to get a simplified picture of the emitted radiation, what we do for the time being, you see, remember what was the radiation, and if you remember the picture, we chose this to be x-axis, this is chosen as x-axis, this is chosen as y-axis, and this was chosen as z-axis, and the charged particle was moving along a circular path in the xz plane, right? Something like this, going like this, xz plane, and this was theta. This is the direction of velocity, this is the direction of acceleration, and this angle is phi, right? So for the time being, let us think in such a way that suppose we are only interested in visualize the radiation pattern in the plane where the orbit is located. So the particle is moving in a circular orbit, and that orbit is confined in the xz plane only. That orbit is confined in the xz plane. So we want to have a view of the radiation pattern in this plane only. So if we want to do that, then we can stick to the phi equal to 0, right? Phi equal to 0 will be xz plane. Of course, you can rotate for the entire phi, but that will be trivial. Once you get the pattern in the xz plane, and then you can rotate that cross-sectional view into the entire space in order to get a three-dimensional picture, right? That will be easier. Okay. So other than looking at different phi and theta, because there can be many different combinations, right? If I go to different theta and phi, there are many combinations, and it will be difficult to visualize. If you want to visualize it, then you have to go to some software and then plot this function to see how it looks like in 3 dimensions. But what I am trying to explain here is a rather simplified view where you stick to a particular plane on which the orbit is confined or located, and then understand how the radiation pattern is looking like. Then you can extend this to 3 dimensions if you want to. But I think this is sufficient to get an idea what should the radiation, which direction gets most radiation, and which direction gets less radiation, and so on. So if I stick to the phi equal to 0 plane, phi equal to 0, that means the plane where this orbit is located, right? So that is the plane of the orbit. Phi equal to 0 means this is the xz plane, or the plane of the plane of the orbit, circular orbit, simply orbit, right? So dp d omega, then what should the expression for dp d omega in that case? So in that case, straightforward, you can see that if I assume phi to be 0, then simply cos phi will be simply okay. How to explain this? Just wait a minute. Okay, so what I am trying to show you is the radiation pattern in the phi equal to 0 plane. Okay, let us go to the next page and simplify this formula. It will take some space. So what was the formula? Let me write down the formula first and then explain it. So dp d omega equal to 1 over 4 pi epsilon 0 q square a square by 4 pi cq into 1 minus beta cos theta square minus sine square theta cos square phi 1 minus beta square divided by 1 minus beta cos theta whole to the power 5. Okay. One more thing I should add here, because you see the entire formula is in terms of beta. Actually, I am not repeating this because these things are quite similar. So in the last class, when we calculated the angular distribution of radiation in case of collinear velocity and acceleration, we also expressed this formula in terms of gamma, if you remember. The thing is quite, very similar. You just write down everything in terms of gamma and then simplify the entire expression. So I'm not going to do that. If you want, you can do that. So I'm just writing, that can be done easily. You can write down this as simply 1 by 4 pi epsilon 0 q square a square by 4 pi c cube. First you take this common, how much this will cancel, 1 minus beta cos theta whole square, 1 minus beta cos theta whole to the power 5. So we'll have 1 by 1 minus beta cos theta whole to the power cube. So I'm taking that outside, 1 by 1 minus beta cos theta whole cube, taking that outside leaves 1 here, 1 minus, you see this is 1 minus beta square, right? This 1 minus beta square is 1 by gamma square. So I can also write sine square theta cos square phi divided by gamma square 1 minus beta cos theta whole square. Why? Because 1 minus beta cos theta whole cube is taken common outside. Actually, you can write down everything in terms of gamma or gamma theta, specifically gamma theta, which I'm not writing. You can, I think this is already done in Jackson's book. If you can see, it is an algebraic exercise where you express everything in terms of gamma into theta. And remember gamma theta, and make a plot of dp d omega versus gamma theta, which we did in the case of collinear velocity and acceleration. It's very similar. So right now I'm sticking to the radiation pattern. Okay, forget about this. Okay, this can be done. I mean, straightforward. So I want to right now discuss about the radiation pattern, how the radiation pattern will look like, right? In case of orthogonal velocity and acceleration. That is our goal. Okay, so first let me, what I told you that phi, we want to visualize the distribution, angular distribution of power only in the phi equal to 0 plane. Okay, phi equal to 0 plane. So we are only interested in the phi equal to 0 plane. That is xz plane, which I told you. And let us do the analysis. Say for say beta is much less than 1. I think yeah, okay, let's write down this for this one first, and then we can simplify. This will be 1 by 4 pi epsilon 0 q square a square divided by 4 pi c cube, and then if suppose beta is much less than 1 for the time, this is an approximation. So we are discussing about orthogonal velocity and acceleration and non-relativistic velocity, right? This we have not discussed earlier. So in case of non-relativistic motion, when velocity is much less than c, velocity is much less than c, and the velocity and acceleration are orthogonal, that is beta is perpendicular to beta dot, then what kind of radiation we should expect? So this is q square a square by 4 pi c cube. Beta is much less than 1, right? So this term becomes negligible. So what we are left with, this is 1, and then we have you see we have already chosen phi equal to 0 plane, so cos square phi will be 1. So we have only sine square theta divided by gamma square, and beta much less than gamma square will be 1, right? So I think no need to write this, right? Gamma will be 1, and this will be again negligible, beta cos theta, because beta is much less than 1, gamma is 1, so we have 1 minus sine square theta. So this gives us 1 by 4 pi epsilon 0 q square a square by 4 pi c cube cos square theta. Now in case of non-relativistic motion with a parallel velocity and acceleration, the kind of radiation we just saw, Larmor formula যখন বার করেছিলাম, this was the acceleration, right? Beta dot, and we defined theta with respect to this acceleration. This was theta, right? And because beta and beta dot were parallel, so no issues, right? And the radiation was entirely confined in this direction, right? Because it was proportional to what? Sine square theta, if you remember. But this time it is cos square theta. That is the only difference. So now velocity and acceleration are orthogonal, and what I am drawing, this picture is drawn on the xz plane, so that you remember the plane of the orbit, phi equal to 0 plane, right? And in this case, suppose the velocity is along this direction and acceleration is along this direction, right? This, you may remember this. Suppose the particle is going like this, okay, touching this, there's a circular path, electron going in a circular path. I'm not drawing the entire circle, right? So velocity is tangential, acceleration is towards the center, beta dot, right? Now you see, you look at this expression. So this is in case of non-relativistic motion, when beta is much less than 1. Both this is when they're collinear, this is when they're orthogonal. So both are non-relativistic. Beta is much less than 1. So in this case, look at this formula. We have simplified this formula for relativistic motion by putting beta much less than 1. We got this one. So now this time it is proportional to cos square theta. It is of course proportional to a square. That kind of dependence is already there, but this depends on cos square theta. And what is theta? If you remember the picture that we have chosen this time, okay, I'm drawing it once again. This was x-axis, this was y-axis, this was z-axis, right? This was our trajectory, right, in the xz plane, right? If you remember, this is the r cap direction, this is theta, this was phi, and z direction is the direction of velocity, beta, right? And x direction is the direction of acceleration, beta dot. So this time, this theta is the angle between this radius vector r and the velocity, right? Now in this case, suppose you want to know what is the radiation along this direction or that direction or that direction, so it is just any arbitrary direction. So r cap is it could be anything, r cap, right? R cap, and the angle between these two is theta. Velocity and r cap is theta. Now, what kind of radiation patterns we should expect? You see, this is cos square theta. So very simple. You see, cos square theta means when theta is around 0, this will maximize power, right? It will be because this term is multiplied with cos square theta. The radiation pattern this time will look like this. In case of non-relativistic motion and orthogonal velocity and acceleration, see, this is the trajectory. So this is a circle. You can imagine a full circle when the charge particle is rotating in a circle. So you expect the radiation pattern coming out of this charge to look like this, right? This is not, so see, this time it was orthogonal to the acceleration. This time also it is orthogonal to direction, but this time so this is the velocity. This time velocity and acceleration are parallel, but this time velocity and acceleration are orthogonal. So the radiation pattern will look like this. So as the charge particle moves from here, it will go like this, right? Or here it will look like this, and so on. So as it moves in a circle, the radiation pattern will look like this for non-relativistic motion. But right now we are discussing about relativistic case. So let us go back to this formula again. Okay, now look at this formula. So what kind of change do you expect if I go to the case when beta is of the order of 1? From this formula we have simplified and got this formula. Look at this formula. Okay, again, okay, cos square phi is of course 1 because phi is chosen to be 0, so cos square phi is 1. Okay, forget about that term. So what are the other things? 1 minus sine square theta divided by gamma square into 1 minus beta cos theta square, right? And this one. So what will happen? What do you expect? So we have something like this. So I'm just drawing one particular picture, and they will be quite similar. So this is suppose I'm drawing the same picture again. This is a velocity, this is acceleration. Perpendicular to that acceleration, and the radiation pattern look like this one, which is parallel to the velocity. Both the forward and backward direction, we get some radiation, and the orthogonal to velocity, you do not see any radiation. এখন এই এক্সপ্রেশনটা দেখো, look at this expression, right? And what can you, of course you can use some software to plot it, but again, I mean, if you can visualize at least some part of it, then it will be useful. So look at this expression. এখানে কি মনে হচ্ছে, যদি এটা নন রিলেটিভিস্টিক রিলেটিভিস্টিক হয়ে যায়, when beta tends to 1, then how should it look like? Should the length of this lobes should be same in both direction, forward and backward direction, or they will be asymmetrical this time? See, in this case they are symmetric. The forward lobe and backward lobe both are identical, but in case of relativistic motion, what I am saying, they will be asymmetrical. But why? Okay, let me just first draw the picture and then explain. Okay, so when you go to relativistic motion, when the velocity is relativistic, what will happen? The forward lobe will be elongated, it will longer, right? It will be longer. So here I do not have much space, so that's why I'm just drawing a picture. Imagine this to be longer than this one. This will be longer as the velocity is increasing, and the backward lobe gets shrinked, so it will be shorter, right? So as you increase the velocity, the forward lobe will be longer and longer, right? And the backward lobe will be shorter and shorter. And in the beta tends to one limit, it will be infinitely long in the forward direction, and the backward direction lobe will be shrink to almost a point, right? So that is the case. But why and how? So let us look at this expression. I already told you that when you stick to the phi equal to 0 plane, this is equal to 1, cos square phi equal to 1. Okay, no issues. Now look at this. And now there are two things. See, when you go to relativistic motion, then of course this one will be, this gamma will be very high, right? Because for say beta equal to 0.99, how much will be gamma, or 0.999. So gamma will increase very rapidly because gamma is 1 over square root of 1 minus beta square. So gamma will be very large. When beta tends to 1, gamma will be very large. So definitely if the numerator denominator is very large, this term will be almost negligible. Of course, there is another term here which you should look at, right? So but since this contains a gamma square, this will be very dominant term, gamma square, and this will this term will be negligible. What about this term over there? This term is, when you multiply first term and second term, this will be there with the both these things, right? So what is 1 minus beta cos theta whole cube? If I look at the forward direction, what is the forward direction? What is the angle in the forward direction? What is the angle in the forward direction?
Theta.
Theta kato? Forward direction? What is the value of
Zero,
theta?
0 degree.
Correct. Theta equal to 0 degree. Correct. So if theta equal to 0 degree and say beta is very close to 1, say okay, for the time being let us take it 0.99. Okay, 0.99 or 0.999. Okay, 0.99 নেওয়া যাক। যদি 0.99 নেওয়া যায় তাহলে 0.99 মানে 1 minus 0.99 কত হবে? cos theta 0, cos theta 0 মানে cos 0 কত হবে? 1 হয়ে যাবে। cos 0 1, so 1 minus 0.99 is how much? What is that? 0.01 cube। তার মানে 10 to the power minus 6, 10 to the power minus 6 তলায় আছে, তাই তো? উপরে গেল কত হবে? 10 to the power 6, তাই তো? 10 to the power 6, 10 to the power 6। তার মানে কি হচ্ছে, এফেক্টিভলি কি হচ্ছে? তার মানে এই টার্মটা বাড়ছে না কমছে?
বাড়ছে, ভেরি হাই।
যদি বিটাটা যদি বড় হয়, বেড়ে যাচ্ছে, তাই তো? দেখো এটা বেড়ে যাচ্ছে। যদি cos থিটাটা 1 হয়ে যায় ফরওয়ার্ড ডাইরেকশনে, এবং বিটাটা যদি ছোট বড় হয়, মানে বড় মানে ক্লোজ টু 1 হয়, 0.99 বলেছি, 0.999 না নিলে আরো বড় হবে। সো দিস উইল বি 10 to the power minus 6 divided by, so this will be actually 1 by 10 to the power minus 6 is actually 10 to the power 6, right? And if you take say beta equal to okay, we are discussing about relativistic motion. Let us now take the backward direction. What is the angle theta in the backward direction?
180 degree.
180 degree. So cos 180 degree কত হবে?
-1
তাহলে এটা কত? 1 plus beta, 1 plus beta। বিটার ভ্যালু কত বলেছিলাম? 0.99। তাহলে কত হচ্ছে? মানে রাফলি 1 plus 0.9 মানে 2, তার মানে 2 to the power cube মানে কত? 8। তার মানে 8 দিয়ে ভাগ হয়ে যাচ্ছে। 180 ডিগ্রি যখন দিচ্ছি ব্যাকওয়ার্ড ডাইরেকশন 8 দিয়ে ভাগ হচ্ছে, এখানে কত দিয়ে গুণ হচ্ছে? 10 to the power 6 দিয়ে গুণ হচ্ছে। তাহলে একটাতে কি হচ্ছে? ফরওয়ার্ড ডাইরেকশনটা it will be amplified and the backward direction will be reduced or shrinked. The size of the radiation lobe will be smaller in the backward direction because of this dependence on this theta, because of this simply 1 minus beta cos theta. So simply theta, when theta equal to 0, this term blows up. I mean, it's not blows up, blowing up, it becomes very large. And when this is small, I mean 180 degree, then you have to divide by some number. So it is just entirely the dependence of this term, which you can plot or you can think. So I just gave you some hint about how to think. So the radiation pattern which will arise from this charged particle in circular motion, where velocity and acceleration are orthogonal to each other, will look like this. And as you go to more and more higher velocity, as it approaches to the speed of light, the forward lobe will be extending up towards infinity, and the backward lobe will shrink almost to 0. So this is the radiation pattern. Okay, so we have discussed about this. And then lastly, I would also like to show you that this how much time do we have? Let me just check. Okay, another 6 minutes. 10 minutes. Another thing that I would like to just show that this distribution that we have obtained from this analysis can be also used to get the Leonard formula that we have derived earlier. Okay, because these are, then you can see that they are consistent. Like it's not like that I get one result for one approach, another result for another approach. No, they are consistent. So how do I calculate total power radiated? Total power radiated can be calculated, total power radiated by the accelerated point charge in this scenario where the velocity and acceleration are orthogonal, and the formula is same, dp d omega integrate over the all solid angle d omega. And what is the formula for dp d omega? We have already calculated this one. What is that? That is 1 over 4 pi epsilon 0. These are constant, nothing to be integrated. Q square s square by 4 pi c cube. And then we have d omega means sine theta d theta d phi. So there are two integral. One is theta integral, another is phi integral. Theta goes from 0 to pi, phi goes from 0 to 2 pi. And dp d omega, I'm writing the expression here. What was that? That was, I'm writing the entire expression, 1 minus beta cos theta whole square minus sine square theta cos square phi. This time I'm not putting phi equal to 0 because this is the integration that we need to carry out. 1 minus beta square divided by 1 minus beta cos theta whole to the power 5 into d omega. What is d omega? Sine theta d theta d phi. And just have to carry out two integral. One is the first integral. You can do it together, but that will be quite lengthy. I think you can divide into two parts. One is 1 minus beta cos theta square by 1 minus beta cos theta power 5. So that will become 1 by that is already done. I think we have already know this part is done. In the previous case, when velocity and acceleration were parallel, we did this first integral, right? So it was let us write down that result. So what we did, we just assumed 1 minus beta cos theta to be equal to x, which gives us sine theta d theta equal to dx by beta. And then you just using the method of substitution, you can calculate these two different sections of the integral, which are these two things, 1 minus beta cos theta. Wait a minute, have I written the same correct expression? 1 minus beta cos theta. What was the expression? Yeah, it's correct expression, 1 minus beta cos theta. Yeah. Again, so everyone of you can do this integration. So this is just a laborious integration which one has to carry out by a method of substitution. 0 to pi, 0 to 2 pi. This is sine theta d theta d phi. And then 1 minus, I think we did it in the last class, one part of it. What is that result? Let us remember. Yeah, sine cube theta. Yeah, this is sine theta or sine cube theta. It was sine, I think it was sine cube theta for okay. I think in this case, one indication will be similar, another will have some difference. So sine theta d theta d phi 1 minus beta cos theta whole to the power 5, right? That was this one, right? Because this cube, this is cube, the first term, because this one and this one cancels out. So 1 minus beta cos theta square divided by 1 minus beta cos theta 5. So this one will be 1 by 1 minus beta cos theta whole to the power cube. And sine theta d phi is there. So I am taking that inside. So this, if you do this integration, this is straightforward to do. This is sine theta d phi, because sine theta d theta is already there. And 1 minus beta cos theta is taken to be x. So x cube dx by beta. Pretty straightforward to do. 2 pi by beta, just 1 minus beta to 1 plus beta, just change the limit, dx by x cube. So what we will get? We will get 4 pi divided by 1 minus beta. So I'm not doing this all the steps here. You can check it by substituting this. We'll get 1 minus beta square whole square. This is the first integral, and the second integral is this one, just this entire thing into sine theta d phi. I think this one. So there is a 1 minus beta square term, multiplied with this 0 to pi, 0 to 2 pi, and then we have sine square theta and sine theta, so sine cube theta, and cos square phi. So there will be two integral, one sine and one minus beta cos theta whole to the power 5 d theta d phi. So carry the integral one by one. First you carry out the integral for say phi or theta, whichever you like. So this will be, for example, if you want to write cos square phi in a simplified manner, you can do 1 minus beta square by 2, and then I write 0 to 2 pi into 1 plus cos 2 phi d phi, and then separate this integral 0 to pi sine cube theta 1 minus beta cos theta whole to the power 5. I think this integral was already carried out in the previous class, this one. So we know the result, 4 by 3 into 1 minus beta cube. And you can carry out this integral, which is straightforward. So 1 minus beta square by 2, this will give us 2 pi, and this will give us, this has already been calculated in the last class, 4 by 3 into 1 minus beta square whole cube. If you simplify everything, you will get 4 pi by 3 into 1 minus beta square whole square, and the integral is actually I1 minus I2, right? There is a minus sign here, minus sign here, so if you put them together, so you will get 8 pi divided by 3 into 1 minus beta square whole square. And finally, if you substitute this the difference between these two integral and multiply with this one, what you get is so if you do the integral which you have shown in the last page, pt equal to 1 by 4 pi epsilon 0 q square a square by 4 pi c cube, and then this will be 8/3 pi, and then what was there, 1 over kichilo 1 minus beta square whole square. 1 by 1 minus beta square is gamma square, so gamma basically 1 by gamma square, so that will be gamma to the power 4. So I can write this to be gamma to the power 4, and if you just cancel this 4, this will be 2, so this will be 1 over 4 pi epsilon 0, 4 pi epsilon 0, 4 pi is there, epsilon 0 there, 4 pi epsilon 0, 1 pi will be cancelled out, pi and pi cancels out, and twice q square a square by 3c cube into gamma to the power 4. This was exactly the Leonard formula in case of orthogonal velocity and acceleration. When velocity and acceleration are perpendicular, we exactly the same this expression from Leonard formula. So Leonard formula, remember the Leonard formula was obtained from a relativistic generalization, and the expression that we have carried out in the last two class are based upon the basically calculation of the radiation per unit solid angle from the expression of electric field and magnetic field associated with an accelerated point charge, and they give us the exactly same result. So these are consistent, and so now we can say that at least we know how or what kind of radiation. How the question how is not discussed much because of the lack of time, and there is a lot of interesting things which can be discussed on this topic. It is a not a very short topic, so I'm not attempting that because at least from the formula you can basically appreciate that the radiation part arises primarily due to the acceleration, which gives a different kind of dependence on the radius vector compared to the usual uniform velocity electric field in case of uniform velocity. So we have seen that there will be a finite amount of radiation for an accelerated point charge at any distances, even at infinite distances, and based on that we calculated the radiation from accelerated point charge in case of non-relativistic motion as well as in relativistic motion, and for two different configurations, specifically for velocity and acceleration when they're parallel and when they're perpendicular. I think I did not have much time today, but I'm giving a few hints here that see, we can easily derive the formula for cyclotron radiation or synchrotron radiation based on these expressions, because you may have heard about this synchrotron radiation or cyclotron radiation. These radiations are basically different names given to the radiation coming out of an accelerated point charge. So when an accelerated point charge is moving with the relativistic velocity, the radiation that we see from the moving point charge are often named as cyclotron radiation. So, and I mean, depending on velocity, whether it's relativistic or non-relativistic, one can call it Brim-Strahlung radiation. I mean, these are basically the kind of radiation that you see in X-ray, right? X-ray is basically the breaking radiation when very high velocity charged particle like electron are deaccelerated. We find some radiation coming out of it in the form of X-rays, which can be called this breaking radiation or Brim-Strahlung radiation. So we shall discuss about a couple of important radiation which are usually talked about in literature and in general in physics. So in the next class. So my plan is the following. So see, we will not be. So what I am trying to do is I shall at least try to cover the radiation part, the main core part of the subject. But there are many other things which can be discussed if we had more time, which we cannot do at this instant. So right now I am discussing about the radiation from an accelerated point charge. But what I left earlier is that discussion about a general charge distribution or current distribution, which can actually give rise to different kind of radiation. I will touch upon that topic at the end of my course. For the time being, we are discussing about a point charge. So let us finish the entire discussion for a point charge first. So in the next, I think 2-3 classes, we shall discuss about this cyclotron radiation, synchrotron radiation, and electric dipole radiation, magnetic dipole radiation. Okay, and one more thing that I think this is a reminder that we have to also complete another tutorial before the class, this exam break starts. So, তোমাদের ক্লাস যেটা আমি বলেছি থার্ড উইক পর্যন্ত ডিসাইড হয়েছে ডিপার্টমেন্টাল মিটিংয়ে, যে থার্ড উইক পর্যন্ত ক্লাস এক্সটেন্ড করা যাবে, তারপরে ক্লাস ব্রেক, এক্সাম ব্রেক হবে এক সপ্তাহের মধ্যে তোমাদের পরীক্ষা শুরু হওয়ার আগে। তো তোমরা একটা মোটামুটি ডেট ঠিক করে রাখো, বিফোর দিস হলেই হবে, ক্লাস বন্ধ হওয়ার আগে একটা পরীক্ষা যাতে দেওয়া যায়। সেটা কবে দেবে, তোমাদের আরো অন্যান্য সাবজেক্টের টিউটোরিয়াল থাকতে পারে বেসড অন দ্যাট। তো আমার মনে হয় যে আমরা একটা টিউটোরিয়াল দিয়ে দিতে পারি। দেখো তোমরা ডেটটা কবে ঠিক করবে। আজকে তারিখ কত? আজকে 10 তারিখ, তাই 10 তারিখ, 15 থেকে 20 মধ্যে একটা কোনো ডেট ফিক্স করে ফেলো। ঠিক আছে?
ওকে স্যার। আর স্যার বলছি ফাইনাল এক্সামটা কবে?
ফাইনাল এক্সাম তোমাদের ফেব্রুয়ারির ফার্স্ট উইক শুরু হবে মোস্ট লাইকলি। ফেব্রুয়ারি ফার্স্ট উইক থেকে সেকেন্ড উইকের মধ্যে সমস্ত পরীক্ষা শেষ হয়ে যাবে। অ্যাকচুয়ালি মানে ইউনিভার্সিটির ইনস্ট্রাকশন ছিল জানুয়ারির মিড থেকে পরীক্ষা শুরু করার, সেটা 1 মাসের মধ্যে শেষ করার কথা ছিল। তো ফার্স্ট 2 উইক পরীক্ষার জন্য ইউজ করা হচ্ছে না, যেহেতু আমাদের সিলেবাস অনেকটা মানে অনেক কোর্সই সিলেবাস পিছিয়ে আছে, সেই জন্য জানুয়ারিটা রাখা হয়েছে মানে ক্লাস প্লাস তোমাদের ক্লাস এক্সাম ব্রেকের জন্য। আর জানুয়ারিটা, ফেব্রুয়ারি থেকে তোমাদের ফার্স্ট উইক থেকে পরীক্ষা শুরু হবে।
ওকে স্যার।
তাহলে তোমরা আমাকে নেক্সট ক্লাসের দিন আমাকে একটা ডেট জানিয়ে দিও যে কোন ডেটটা তোমাদের জন্য কনভেনিয়েন্ট। আমি একটা আরবিট্রারি চাপিয়ে দিতে পারি, চাপাচ্ছি না এই কারণে কারো তোমার সুবিধা হবে, কারো অসুবিধা হবে, তোমরা ডিসকাস করে আমাকে জানাও। তোমরা যদি নিজেরা ঠিক করতে পারো তাহলে ভালো, আর তাহলে আই হ্যাভ টু ডিসাইড নেক্সট ডেটে তোমরা জানিয়ে দাও। আচ্ছা, কোনো কোয়েশ্চেন আছে? ওকে, ঠিক আছে, তাহলে we shall meet again in the next class.